Hello everyone, welcome back. Now let us see the lesson number 10 of Unit 1 from Signals and Systems. In this lesson, we are going to cover orthogonality in complex functions. As you know, the complex functions, how they are represented, a plus jb or a plus ib. So similarly, for orthogonality condition, how we are obtained for vectors or signals or for an infinite series. Similarly, for a complex function, we are going to obtain this orthogonality condition. So from this lesson, students will be able to express the orthogonality for complex functions and derive the approximate original orthogonal function. So consider x1 of t and x2 of t are two complex functions of real variable t. x1 of t can be expressed approximated by c12 and x2 of t or an interval x1 or interval t1 to t2. So as we already discussed, expressing signal in terms of other signal. So here we are expressing x1 of t in terms of x2 with the parameter c12. So c12 will be your magnitude and x2 of t is the other complex function. So the optimum value of c12, that is the minimized value of c12, need to be represented so that the minimum mean square error will be 0 or nearer to 0. So as from the expression we already got from the C12, that is integral of x1 x2 dt by integral of x2 square. So similarly here also, as we are expressing for a complex function, the value of C12 is given as integration of t1 to t2 x1 of t into x2 conjugate of t into t2. So x2 star nothing but x2 conjugate. Similarly, the denominator side is given as integral t1 to t2 x2 of t into x2 conjugate of t into dt. So please remember that x2 conjugate is the parameter that is represented in the numerator side and also at denominator side. Okay, x2 conjugate nothing but if I express x2 of t as a plus jb, x2 conjugate of t will x2 conjugate of t will be a minus jb. That's right, a minus jb. For the complex functions to be orthogonal over the interval t1 to t2, the value of c12 must be 0 for to satisfy the orthogonal. So similarly, the value of c12 if I express or equal to 0, the above expression can be represented as this term is equals to this term. So I have rewritten that one and equated to 0. Okay, next one. For a set of complex functions, say gr of t, where r equals to 1 to so on up to infinite, the mutually orthogonal over the interval t1 to t2 can be given as gm of t into gn conjugate of t. So please remember it is a gn conjugate of t. The expressions are similar to previous lessons, but here we are considering for a complex. So we need to represent a conjugate term as a second term and the normal in the first term. So integration is normally from t1 to t2, gm of t into gn conjugate of t into tt is equals to 0 if m not equals to n and equals to some value if m is equals to n. Okay. If this set of functions is complete, then any function x of t can be expressed as. Similarly, the last 2 points are coming from the previous lesson itself. To be a complete set, the value of x of t must be defined from c1, g1 of t, and so on for different signals with respect to the magnitudes. And the magnitude value of CR is given as 1 by KR integral T1 to T2. Here we can represent either KM or KR depending on our GR function. So here we are expressing with the CR, so I am writing as KR. Can either represent with KM also, so that the value here we need to write as CM. So it's C suffix M. If I want to express K as K suffix M, we need to express K suffix. If we are expressing with respect to suffix as M, the C value need to be represented with C suffix M. Similarly, I am representing with K suffix R. So here it will be C suffix R, which is given by 1 by KR integral T1 to T2 x of t into gr conjugate of t into dt. Okay, you need to remember these functions, how we are going to express and how or on what basis the signal x of t is expressed in terms of g of g1 of t, g2, g2 of t, and so on. So please remember the signals or the vectors that are being represented so that they can be orthogonal, or they how they're going to be orthogonal, on what conditions we are going to make them as an orthogonal. So this is how we are discussing it now. That is how the lesson 10 will be completed. We'll see in the next unit of how these formulas we are going to use. Thank you for listening. Thank you.